Hi, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 4. In this lecture, we'll discuss position, velocity, and acceleration. These topics are covered in Chapter 2 of our textbook by Surway and Jouet. In general, we'd like to study the motion of objects. In fact, the study of motion is an important and fundamental aspect of physics. To study the motion of an object, we need several variables, often referred to as motion variables, to describe its motion. These variables are position, velocity, and acceleration. We'll have to speak of these individually in turn. Of the three, perhaps the most important quantity in describing the motion of an object is the position of an object. So let me start by giving you a formal definition of what position means in physics. Position is the location of an object in space with respect to a coordinate system. So notice that position and location are similar in meaning, except that when I ask you what is the location of an object, you can just point to it and say the object is there, for example. But when I ask for the position of an object, you'll have to give me a location with respect to a coordinate system. So a coordinate system is a necessary prerequisite for defining the position of an object. For example, if I said, where is the car in this picture? You could simply point to it and say the car is there. But if I ask for the position, you would first have to set up a coordinate system, meaning that you would have to choose some point as the origin, as 0. Then you would have to choose some kind of a scale so that you can lay down markings every, let's say, 1 meter or every mile or every kilometer. And then in reference to that coordinate system, you can say that the position of the car is 4, let's say. We usually denote position using the letter x, so we would say that x equals 4 denotes the position of this car. Now, notice that one could also use a different coordinate system. For example, you might say, well, I want a coordinate system whose origin is, for example, where the car is located. In this second coordinate system near the bottom, we've located the origin where the car is, and so in this coordinate system, the position, x, is equal to 0. So there is a little bit of ambiguity or arbitrariness in what position is. It depends very much on the coordinate system. So going forward, whenever we talk about the position of an object, keep this in mind, that you must have a coordinate system determined before you can sensibly talk about the position of an object. We should also mention that position is a function of time. I suppose if the car is just parked there on the street, then its position is not changing. But in a more interesting example, the car would be driving around, so its position would change. 1 second it might be here, the next second it might be here, a few seconds later it might be here. And we express that fact by writing x as a function of time. Here we're saying that position depends on time. Depending on what time you want to talk about, you might have a different position. Now, if x is a function of time, one useful way of representing motion is to make a graph or a plot of position versus time. We'll encounter graphs of position versus time frequently throughout this course, so it's important for you to be able to interpret these graphs. Here, what you see is a graph of x as a function of t. Notice that this is a little bit disorienting because we're placing the variable x on the vertical axis, and on the horizontal axis we have t. This is a little bit different than the convention that you may have encountered in your math class, where on the vertical axis we are representing y, and on the horizontal axis we're representing x. The important thing is that in this context, when we're discussing the motion of objects, t, or time, is the independent variable, so that goes on the horizontal axis, and the position, or x, is the dependent variable, so that goes on the vertical axis. If I give you a graph of x versus t, and I tell you that the graph looks like this, essentially a horizontal line, you should understand that this graph represents an object that is basically stationary at x equals 5. If I asked you what's the position of this object at t equals 0, you would say 5. If I said what's the position 2 seconds later, you would say 5. And if I said what's the position at 10 seconds, you would say 5. So this is the graph that represents, for example, a car that might be parked on the street at coordinate x equals 5. Not a very exciting example. Here's a slightly more interesting example. What is this graph representing? What type of motion are we talking about here? Well, at t equals 0, x is equal to 0. But 2 seconds later, we can see the object must have moved. It has moved to x coordinate 2.5. And 2 seconds later, it has moved further. And at 10 seconds, it is now at an x coordinate of 10. So clearly, this is an object that is moving. We can even say that it is moving forward in the sense that its x coordinate is increasing. A little bit later, we'll quantify this motion even more precisely. We can talk about the speed or the velocity. But for now, when you look at a graph like this, you should be able to read off the position as a function of time and at least verbally describe this motion as the motion of an object that is moving forward. Here's another graph of position versus time. In this case, we can see that the object was located at x equals 0 initially at t equals 0, but as time wears on, you can see the x coordinate becomes more and more negative. So the object starts at x equals 0, and then it gradually goes to minus 2.5, and then 5, and minus 7.5. And finally, after 10 seconds of motion, its x coordinate is minus 10. Clearly, this is an object that is moving, and we can say that this object is moving in the negative x direction, or just more simply, the object is moving backwards. This is still a relatively simple example. By the time we're done with this topic, we'd like to be able to analyze complicated graphs like the one shown here. This is clearly an object that is moving forward and backward. As you can see, the object starts at x equals 0 initially, and then it goes backwards for some time, for maybe half a second or so. Its x coordinate becomes minus 2.5, and then minus 5, and then maybe minus 7.5, and maybe even minus 8 or minus 9. And then the object begins to move forward. As you can see, its x coordinate is now increasing. All the way up to about 2 seconds, the object is moving forward. Its x coordinate increases all the way to about 5. And then for whatever reason, the object begins to go backwards again and then forwards again. We'd like to quantify all this much more precisely a little bit later, but for now, when you look at a graph like this, you should be able to indicate that it is moving forwards and backwards, and you should also be able to tell me when it is moving forward or when it is moving backwards. If I ask you what is it doing at 5 seconds, you should be able to look at the graph and notice that at 5 seconds, the x coordinate is increasing, so the object is moving in the positive x direction, and therefore you can say the object is moving forward. A little bit later, we'll see that we can also look at the slope of a graph like this and figure out precisely how fast it is moving forward or backward. As we've been saying, the position of an object can change as a function of time. So often we'd like to know how fast the position is changing. More precisely, we'd like to know the rate of change in position. Velocity is the rate of change in position. Velocity can be thought of as the speed of an object. The speed of an object is the thing that tells us how rapidly or how quickly or how fast the position is changing. For now, you can think of velocity and speed as synonymous. A little bit later, we'll discover that there is a subtle difference between velocity and speed, but for now, if you want to think of velocity simply as the speed of an object, I think you should be safe. There are two types of velocity that we'll want to talk about. There is average velocity and there is instantaneous velocity. Average velocity is delta x over delta t. In general, this notation delta refers to the change in some quantity. So what we're imagining here is an object that is located somewhere at some time. We'll call that initial time, initial position. And the object moves, and a few seconds later, at some final time, it will be located at some final position. So what we have here really is a change in the position, which if you want, you can write as x final minus x initial. And then we have a change in time, and if you want, you can write that as t final minus t initial. So we have an object that was located at coordinate x initial at some time, t initial. That initial time is often chosen to be 0, but it doesn't have to be 0. And then a few seconds later, like 12 seconds later, its position will have changed to x final. And so what we have is a change in x and a change in time. That's what the delta denotes. And the ratio of those two changes is what we refer to as the average velocity. You can see if delta x is large, that means the position has changed by a large amount, then the average velocity is going to be a large number as well. So the speed is large. On the other hand, if delta t is large, so it took a long time for the position to change, then the average velocity will be small. So the object is moving slowly, its speed is a small number. Now note that average velocity refers to some finite length of time, some duration, some time interval between initial time and final time. Sometimes we're not interested in how fast the object is moving over some duration of time. Often we're interested in what the velocity is at a single moment in time. That's referred to as instantaneous velocity. To calculate the instantaneous velocity, we basically take the average velocity, delta x, divided by delta t, and we take the limit of this ratio as the denominator. Delta t goes to 0. This should make sense. After all, we're talking about an instant in time. How long does a single instant in time last? Well, 0 seconds. You can think of an instant in time as maybe a millisecond, or a microsecond, or a nanosecond. An instant in time really is an infinitesimal quantity, and that's what this limit, delta t goes to 0, is indicating. Hopefully you remember from your calculus class that when you take the limit of a fraction as the denominator goes to 0, what you get is a derivative. In fact, that's how a derivative is defined. We write that derivative as dx over dt. So dx over dt denotes the derivative of x with respect to time. In your math class, you may have written this quantity as x prime, where the prime denotes the derivative with respect to time. However, the prime notation can get a little bit confusing in physics because we'd like to take derivatives with respect to other variables. So in physics, we often use the so-called Leibniz notation, where the derivative is written quite explicitly. So dx dt has very little ambiguity in it. It's your instruction to take the derivative of x with respect to t. As I mentioned before, we often like to represent motion using graphs. So here we have a graph of x versus t. And you can see that this object is moving forward from 0 to 4 seconds, and then it begins to move backwards from 4 to 8 seconds, and then at 8 seconds, it basically stops and its coordinate remains constant. Looking at a graph like this, we can tell whether it's moving forward or backwards, and now that we know about velocity, we can also tell how fast it is moving forward or backwards. If you want to calculate the average velocity, you need to calculate delta x and delta t between 2 points on the graph. So you might be interested in, for example, this point and this point over here. You can calculate delta x. I can see that, for example, x initial is equal to 4. I'm reading that off of the graph here. And at this point, I can see that x final is equal to minus 4, again reading that off the graph. I also need initial time and final time. I can see that t initial is equal to 4. And I can see that t final, reading it off the graph again, is equal to 8. Now that I have these two quantities, I can calculate the change in x, I can calculate the change in t, and the ratio of those two changes would give me the average velocity. You can also calculate the instantaneous velocity at a single moment in time. You might be interested in knowing what the velocity is at this point, at t equals 6 seconds. In that case, you want to look at the slope of this line at exactly 6 seconds. Hopefully you remember from your calculus class that the derivative of a function is in fact the slope of the tangent to the graph of that function. The position of an object can change, and if you want to know how fast the position is changing, then you need to know the velocity. It turns out that the velocity of an object can also change. When you're driving your car and you floor the gas pedal, if you look at the speedometer in your car, the speedometer is measuring your speed or velocity. If the needle on the speedometer is racing upwards, then your velocity is changing. And often we want to know the rate at which the velocity or the speed is changing. It turns out the name of that quantity is acceleration. Acceleration gives you the rate of change in velocity. Acceleration tells you how fast or how quickly the velocity of an object is changing. Just as there were average velocity and instantaneous velocity, we have two kinds of acceleration, average acceleration and instantaneous acceleration. Average acceleration refers to the change in the velocity of an object. To calculate this, you need to take the difference between some final velocity and some initial velocity. And also you need to know what the final time and the initial time were. The ratio of these two changes gives you the average acceleration. Average acceleration refers to some finite duration of time, some time interval delta t. This might be a few hours or a few minutes or a few seconds. But if you're interested in the acceleration at a single moment in time, then delta t has to be a very, very small number. To be a little more precise, we need to take the derivative. We need to take the limit as delta t goes to 0, and this particular limit gives us the derivative. Sometimes people write the derivative of v with respect to t as v prime, where the prime again indicates a derivative. However, in physics, we prefer this Leibniz notation. It's a little more explicit. dv divided by dt is telling us to take the derivative of v with respect to t. We sometimes represent the motion of an object using a graph of x versus t, but we can also draw graphs of v versus t. Notice this particular graph is a little different than the graphs we've been seeing so far, because what we're plotting on the vertical axis is the velocity of the object versus time. So as you look at these graphs, first and foremost, look at how the axes are labeled, because an x versus t graph gives you a different piece of information than a v versus t graph. Here what we're seeing is an object whose velocity initially was 0, and then the velocity gradually increases, and it becomes 2, and then 3, and then 4, and then the velocity remains constant. The object is moving, but its velocity is not changing. And then if this is, for example, a car, we can imagine that the driver is applying the brakes, and so the velocity drops down all the way to 0 at this point here at 9 seconds. And then you can see after that the velocity actually becomes negative. So at 10 seconds, the velocity is -2, which means this, let's say, car is moving backwards at 2 meters per second. If you are given a graph of this nature, velocity versus time, and you want to know what the acceleration is, you need to calculate the slope. You can calculate the slope by looking at the rise over the run. Delta v is the rise, change in the vertical axis, and delta t is the change in the horizontal axis. Or if you want to know what the instantaneous acceleration is, then you'll have to take the derivative at a particular moment in time. For this particular example here, if I said what is the acceleration at 5 seconds, you would have to calculate the derivative at this particular point. You can see that the line is horizontal. Hopefully you remember that the slope of a horizontal line is 0. If the slope is 0, then the derivative must be 0. So at 5 seconds, we can say dv dt is equal to 0, which tells us the acceleration must be 0. So at 5 seconds, the car is not accelerating, it's not going faster, it's not going slower, it's maintaining a constant velocity. Let's do a practice problem involving some of the concepts we've just learned. The velocity of a particle is described by this particular function, minus t squared plus 10t. Let's assume that all of the quantities involved are in SI units, so we don't have to do any conversions. The first question is, what is the position of the particle at t equals 12 seconds? Okay. First and foremost, notice that I'm not providing the position as a function of time. I'm providing the velocity as a function of time. So using this function, you could figure out how fast the object is moving. You can figure out its speed at any given time. You would just plug in t in here to find the velocity. And the question is asking for the position. You should be recalling at this point that we defined velocity as the derivative of position with respect to time. And this should indicate to you that if you are given the velocity and you want to calculate x, you should probably do the opposite of differentiation, and the opposite of differentiation is integration. So if velocity is the derivative of x with respect to time, then position is the integral of v with respect to time. If you want, you can also make a graph of the function that's shown here. You can see that the t squared indicates a parabolic graph because there is a minus sign in front. It's an inverted parabola, so it's an upside down parabola. And more precisely, if you have a graphing calculator or you know how to use a graphing program, you can make a graph of it, and the velocity versus time graph would look like the parabola shown here. At any rate, to calculate the position of the particle at 12 seconds, what we need to do is take an integral. Remember from calculus that integration is the opposite of differentiation. A little more precisely, we need to take the integral of v with respect to t between initial time and final time. So we're going to start at t equals 0, and we're going to end at 12 seconds because that's the time that's given to us in the problem. We need to now take this function here and integrate it. This is a second order polynomial. Hopefully you remember how to integrate a second order polynomial. You can use the power rule for each term in the polynomial. The integral of minus t squared becomes minus t cubed divided by 3. And the integral of 10t becomes 10t squared divided by 2. And that gives me 5t squared. So the integral is minus 1/3 t cubed plus 5t squared. And then, of course, don't forget the limits of integration. The limits are 0 and 12. In physics, we normally prefer doing definite integrals. In other words, we usually would like to know what the limits of integration are, and we would like to plug those numbers in. So now we have to plug in 0 and 12 into our integral. And when we do that, we find 144 meters. This is going to require that you plug some numbers into your calculator. You need to be relatively comfortable with this type of a calculation. So finally, we can say the position of the particle or this object after 12 seconds is 144 meters. If I'd asked for the position of the particle at, let's say, 7 seconds, then the limits of integration would be 0 to 7. Here's part B of the same problem. Again, we have a particle. Its velocity is described by this function here. This is exactly the same function you saw in the previous slide. But this time I'm asking you a slightly different question. I'm asking for the total distance traveled by the particle at 12 seconds. On the previous slide, I asked for the position, and now I'm asking for the distance. Answering this question requires that you think a little bit about the distinction between distance traveled and position. Distance isn't always the same thing as the change in position. If you get in your car and drive down the street by 100 meters and then realize that you've forgotten your keys, you might put your car in reverse and go back 100 meters. In that case, your initial position and final position are the same. You started at x equals 0 and then you ended at x equals 0. So the change in position would just be 0, as in 0 minus 0. But of course, the distance traveled is a little bit different, right? You moved forward 100 meters and then you stopped, put the car in reverse, and you went backwards by another 100 meters. So the total distance traveled would be 200 meters. For example, if you're trying to figure out the amount of gas consumed by your automobile, what you're really interested in is distance, not so much position. So if you look at the graph shown here, you can see that this object is going forwards and backwards. This is an object that starts at with a velocity of 0. Note that this is a velocity versus time graph, not a position versus time graph. According to this graph, the velocity increases all the way to 25 meters per second. And then it seems like the object is slowing down. It's still moving forward. It's moving forward because its velocity is still positive. It's just moving forward more slowly. And then finally at 10 seconds, the velocity is 0. That indicates to us that this object must have stopped. And then its velocity becomes negative after 10 seconds. That tells us that the object is moving backwards. So if we're going to calculate the total distance traveled by this particle, we have to be careful. We have to treat this problem as a two-stage problem. We need to figure out the distance traveled from 0 to 10. And then after 10 seconds, because the object is moving backwards, we have to be a little careful and figure out the distance traveled between 10 and 12 seconds and then add those two distances together. Another way of saying the same thing is to say that distance is basically the integral of speed with respect to time, but it's the absolute value of speed that we care about. When it comes to distance, we don't really care whether the object is moving forward or backwards. It's simply the absolute value, that positive number representing speed. Now, to calculate an integral involving an absolute value in it, you need to recall an important fact from your algebra days. The absolute value of some number a is equal to plus a if a is a positive number, but the absolute value of a is equal to minus a if a is a negative number. So if a is, for example, minus 5, then its absolute value is going to be equal to minus a minus 5, which would give us 5. Remember, the absolute value sign always results in a positive number. Why is this little fact important to us? Well, because we're interested in the absolute value of v, and I can tell you that the absolute value of v is simply equal to minus t squared plus 10t. That's the function that was given to you here, between 0 and 10 seconds. But after 10 seconds, between 10 and 12 seconds, because the velocity becomes negative, I need to take the original function and multiply it by a negative 1. If I take this original function and multiply it by minus 1, I get t squared minus 10t, and that's where this function comes from. So I need to now do an integral, but because we decided this is a two-stage problem effectively, we're going to do two integrals from 0 to 10 and then another one from 10 to 12. The integral from 0 to 10 is going to involve an integral of this function here, whereas the integral from 10 to 12 is going to involve an integral of this function over here. Notice the two functions aren't very different, there's just a minus sign in front of them. Just as here we have plus a and minus a, the only difference is simply the negative sign. When you perform those two integrals, you get these two functions. Don't forget the limits of integration from 0 to 10 and then 10 to 12. Put those limits of integration in using your calculator. For the first integral, you will see that the object travels 166 meters approximately. And during the second stage, between 10 and 12 meters, the object is traveling 22.6 meters. If you want, you can say during the first 10 seconds, the object is moving 166 meters forward and then 22 meters backwards, approximately. And if you add those numbers together, notice those are both positive numbers, what you get is 189.3 meters. The bar over the 3 simply indicates a repeating decimal, so a more exact answer would be 189 and 1/3 of a meter. And that's the end of this lecture. Thank you for your attention.